Good morning, class. My name is Cole, and today we're going to be answering questions on clustered, regularly interspaced, short palindromic repeats, also known as CRISPR. So, what exactly is CRISPR? Well, CRISPR is a cluster of repeating DNA that is found in a bacteria. It was originally found in some type of bacteria that represents something close to E. coli. It's currently thought of as like the innovating gene for editing, as the DNA pattern allows scientists to manipulate other strands of DNA. It was originally discovered by the Japanese scientists, as you can see in this photo. I would say his name, but it is quite difficult for me to say. Um, However, they had not understood uh, the significance behind the gene editing. Now, how exactly do these scientists use CRISPR to manipulate DNA? Well, these scientists achieve this by introducing this shown on the screen right here. This is the Cas9 protein. It's used to target the DNA strands that will undergo the genetic modification. All right. So Cas9 is a protein that is driven by CRRNA. All right. The Cas9 protein then binds to a new nucleic acid and snips the ends of the DNA strand. With this being said, the Cas9 protein acts as the scissors in the genetic modification process, removing DNA strands from the equation. The process would look something like this. All right. Now, following the removal of the DNA sequence, how does the CRISPR-Cas9 system replace the SNP DNA sequence? So, the Cas9 protein is not limited to the removal of DNA sequences. The Cas9 protein incorporates cRNA and tracker RNA, which will generate portions of DNA strands. These newly generated DNA strands are called DSB, or double-stranded breaks. Uh, this DSB will then take its respective slot into the original position that the first DNA strand was holding. As you can see, the gap in the lower area of the DSB. Now, how do the pros and cons weigh out when considering genetic editing? Well, here are the pros. The biggest concern is the ending of suffering. Some individuals possess genetic mutations that can cause immense suffering. These individuals are born with mutations and don't suffer because of their own choices. Uh, in one example, as you can see on the screen, we have sickle cell disease. Sickle cell disease is a genetic disorder where the individual's blood cells form in abnormal shapes and they clog the capillaries. Sometimes they even cause organ damage and heart failure. By disposing of this genetic strand that codes for sickle cell disease and coding for the opposite, this causes the individual's pain to subside. However, a huge setback that I've seen is the cost of CRISPR operations. Although they are life-saving, they come at a steep price. According to the National Library of Medicine, one of the first FDA-approved CRISPR operations is estimated to cost anywhere from $4 to $6 million. Although it is for lifetime treatment of neurodegenerative cerebellum disease, it is still $4 to $6 million. Now, other things that I've seen that can really cause setbacks is healthcare disputes that happen between the lower and the higher class, due to the higher class being able to afford such healthcare that can provide these operations, while the lower class couldn't, meaning they just suffer due to the fact that they have less money or worse healthcare. As for the risks of genetic modification, the main risks associated with genetic modification is off-target genome editing, and the effects that come with that. According to UCLA Research Safety and Animal Welfare Administration, the off-target effects are due to incomplete homologies between gRNA and other regions of the genome. At this time, there is no known reverse for the cause of these off-target effects after exposure to the procedures. Um, Worth it. Well, that's up for you to decide. However, these results are not guaranteed when the procedures are done and can cause serious repercussions if they are executed poorly. And CRISPR is relatively new to the medical world, being introduced around a decade ago. However, the benefits we've seen so far have made it pretty clear to me that there is an extreme amount of potential in these operations. Within a decade of discovery, CRISPR has not only been found to cure sickle cell disease, but has also been utilized to help treat cancer. Uh, the risk of the unknown should not fear scientists from straying away from CRISPR or genetic modification. Um, from trial and error, that is how these operations will become complete and utilize less risk over time. Ethicality. This is something that should always be considered when the lives of masses of people and animals are at stake. It is a wild conjecture to expect every experiment to go flawlessly the first time through. No steps forward can be taken without taking a few steps back. All right. In the field of genetic modification, the process is extremely difficult to understand. It has taken from 1980 of the discovery of CRISPR to 2012 to implement a single process. However, this single process has already saved thousands of lives, and it's been groundbreaking treatment to support the cure of these diseases. So that's up for you to decide, but I believe it is ethically sound. And here are my references. If you have any questions at any time, feel free to utilize these. Thank you.